Welcome back. Today we're going to talk about horizontal projection. This is continuing our Unit 3 work on gravity from the Queensland Physics syllabus. Okay, a few things to get you thinking about what's going on here. You can see that nice little GIF there of that hammer throw that seems to not be working very well. The question above there is, does the hammer continue in a circular path for a fraction of a second after it's let go? What we're saying is if we're swinging a hammer in a circle, then should it continue in a circle when you let it go? And you can see the moment she lets it go, it flies off into the official, which is very unfortunate and not funny at all. Next part there, do bombs and bullets fired at 45 degrees have the greatest range? Well, we started looking at this sort of thing in last episode, but what we'll see is that yes, 45 degrees is theoretically the greatest range possible for a projectile. However, in the real world, we have air resistance to contend with as well. All right, so we're chugging through our list here. This comes from our curriculum. We've definitely ticked off the first two. We've started discussing the third one. Today, we want to start looking at some of these formulas that we're going to implement and do some calculations with them. So we're going to investigate projectile motions by combining vectors, and we will be able to calculate components of motion. We'll be able to describe the motion of an object based on the vectors that we can resolve. So in projectile motion, we tend to look at these two sort of scenarios where an object falls off a high place like a cliff or a desk or something like that. In that scenario, you can see that the ball is traveling horizontal and it doesn't have a vertical component to its motion, as opposed to the other scenario where we have an angle of projection and it can be resolved into uy and ux, two different components there. So consider when a ball is thrown or something like that, does the gravity ever switch off? Well, here on Earth, no, we tend not to turn off gravity. So the ball is always influenced by acceleration due to gravity, and we tend to get an arc that the ball tends to go in like that, as you just saw in that little animation. Remember, the idea of a reductionist approach is that we break the components into the two independent parts, the vertical component and the horizontal component, and they do act independently of each other. If I look at the little scenario there, I have independent components for both vertical and horizontal at each time. Notice that my vertical component here, uy, decreases to 0 up the top there, and then ends up as the same magnitude in the opposite direction down the bottom there. So that would be vy, v being the final velocity. Notice my x direction, there's no acceleration there, so it's not changing. We'll talk about that in just a sec. So projectile motion is the whole field of studying objects which travel with some initial velocity and are acted by acceleration due to gravity. We can look at this sort of scenario in other situations, but we tend to concentrate on Earth type situations here, and gravity being the only sort of accelerating force, although the same principles do apply in other scenarios elsewhere in the universe. Now, gravity is only ever acting in the vertical direction on the y-axis, all right? But in order to do this, we have to set ourselves up with some vectors, so we have to set up ourselves a base reference. So we tend to say that up is positive, to the right is positive, so any sort of negative velocity would be going down or to the left. So remember, acceleration due to gravity on Earth, which is what we're calling AY, it's only happening in the vertical direction or the y-axis, is negative 9.8, and it's negative because it's acting down. Now, we often assume that there's no air resistance because we live in Fantasyland, but the reality is it makes our calculations easier. So in the horizontal direction, there is no acceleration at all. So that's why we're saying that ux equals vx. And if we think of our formulas that speed is distance over time, so instead of speed, I'm going to talk about velocity, and I'm going to talk about an initial velocity, and it's going to be in the x direction. And instead of a distance, I'm going to talk about a displacement. We end up with this little formula down the bottom here. So Sx equals uxt. The horizontal displacement, that's Sx, is the initial velocity in the x direction times the time that this object's in motion. Fairly straightforward. So all objects are released at the same time with no initial velocity in the y direction will hit the ground at the same time. It doesn't matter what their horizontal velocity is, they hit the ground at the same time. We're going to look at some quick animations to show us that. So, see there, this object fell straight down. This one had a horizontal velocity, but as far as we're concerned, the velocity in the y direction was the same for both of them, so they both hit the ground at the same time. If we look at Stickman physics, he drops a ball, 0.76 seconds. Does the same thing, but gives it a horizontal component as well, but the vertical component has not changed, so it is still operating independently, therefore it's still hitting the ground at the same time. So, simplest case of projectile motion is when the initial velocity is only in the horizontal direction. There's nothing in the y direction, such as our example there, rolling a ball off a desk, dropping a rock off a cliff. I'm sure it's a lot of fun. So to solve these, we'll tend to use our Suvat equations that they're called. But we'll concentrate on the two that we showed on the previous slide in the red boxes first before we get onto the other components. But don't forget, we're always resolving components into x and y. Now, the link, this is the important point here. The link between horizontal and vertical components is time. Whilst the acceleration is different in x and y, initial velocities are different in x and y, the displacement's different in x and y, the one thing that's common between x and y is time. So usually finding the time that this object's in motion will help us move between x and y components. And we'll look at some examples of that. All right. Here's the same sort of thing again. Notice that we have two objects falling. On the left-hand side here, the red ball has no horizontal motion, only vertical. The blue ball's got a horizontal component as well, but as far as we're concerned, in the y direction, the vertical direction, it's still falling at the same rate. Same over here, you can see the same deal. The vertical velocity is increasing, and that vector is getting larger and larger and larger until we get down the bottom there. All right. Horizontal displacement of an object is often called the range. How far we go sideways is often called the range. All right. We're looking at this scenario where the initial velocity in the y direction is 0, so it's something that's literally being dropped. We're dealing with this guy here and this guy here. This table over there on the right comes from the Formula Data book, and I do encourage you to familiarise yourself with that prior to getting to exams. All right, let's look at some examples. A golf ball is projected horizontally off a cliff at 20 metres a second, and it takes 4 seconds to reach the ground. So this here will be our initial velocity in the x direction. Our initial velocity in the y direction is 0 because there is no vertical velocity there. It's literally just a golf ball hit with a club straight off the cliff, and it's going directly horizontal when it starts. And time is 4 seconds. Calculate how far out from the base of the cliff the ball will land. So that will be Sx, our horizontal range. Here's our cliff, here's our golf ball. It's projected out that way at 20 meters per second. It's going to fall out down here, and I have this distance here, Sx, the horizontal range. That's what I want to find. So, as you can see here, we've written down our unknowns. Go back and look at the formula book, pick the one that works. If I've got this guy here, and I've got this guy here, and I want to find this one here, literally match it up to the formula book and find out which one works. Sx equals uxt, and I plug my numbers in. Initial velocity is 20 times 4. 20 times 4 is 80 meters. I'm not using kilometers an hour or anything like that. I'm using standard units, and my horizontal range, the distance, comes out in standard units, which is meters. So the ball lands 80 meters out from the base of the cliff. Right, let's look at more equations. Now these ones, you notice all have little subscripts for y, because these are all our equations we use in the y direction. And it's the equations that we should be familiar with by now. So V equals U plus AT is that first one there, but we're just saying V in the Y orientation equals the U, the initial velocity in the Y orientation, plus AT, but A in this case is G, acceleration due to gravity. They come from the formula book. Write them down, be familiar with them. You have to know how to use them. All right, example time. So golf ball. What are we doing? From the previous example, the one that was struck out from the cliff, we're looking at the final velocity, the final impact velocity, and the height of the cliff. So when we're looking at part A there, I hope you don't play golf like that guy down the bottom there. Anyway, when we look at letter A there, the final impact velocity in the vertical direction. So in that case, we're looking at the final velocity, which is V in the Y direction, and we want to find the height of the cliff, which will be the vertical displacement in the Y orientation. As it says there, our term used here, or the cognitive verb in the question, is calculate. So calculate just means we want to work something out. We're going to use some math stuff to work something out. Righto. Notice here we've written down what we need to know. We've written down what we need to identify, what we need to find. Literally look at those variables, look at your formula book, and work out which formula is going to match. I have an initial velocity in the X direction. I have an initial velocity in the Y direction of 0. I've got time. I've got acceleration due to gravity. Let's find what else we can. Plugging all those into a formula, what do we get? V equals U plus AT, or Vy, final velocity in the Y direction, equals Uy, initial velocity in the Y direction, plus G, acceleration due to gravity, times the time. We know how long the time was because it told us in the previous second. It was 4 seconds. Plug your numbers in and put it in your calculator. It'll all come out in the wash. What do we get? So negative 39.2. Notice my acceleration was negative on that previous slide, which gives me a negative velocity here, which tells me, remember, if my up and to the right is positive, then this is a negative one in the Y orientation, which means my velocity is downwards. Right, next point, next one, part B, we've got to find the horizontal range. So S is equal to UT plus a half AT squared is our formula. Notice what we've changed, SY, displacement in the Y direction. That's how high the cliff is that this thing was hit off, equals Uy, the velocity in the Y direction, the initial velocity in the Y direction, but that's 0, times the time, which we know, plus a half GT squared, G being gravity. And it's pretty straightforward. Plug your numbers in. If you need to pause the video and look at where those numbers came from and where they go into, have a quick crack at that now. But when we plug it in, notice our negative 9.8 in there will give us a negative range, or sorry, a negative displacement, which means that we're falling down the cliff. It means that we're standing on top of the cliff where the ball's hit and it's going down 78 meters. That's the height of the cliff. If you want to pause the video and have a go at the questions down the bottom there, do that right now. Okay, let's keep going with this one. Goodness me, don't be like that guy there. I mean, I don't know, maybe you love pink pants, but I don't know. Don't fall in the water like that. What are we doing here? The golf ball that is struck off the cliff strikes the ground, has a final velocity in the vertical direction of 39, so that would be Vy. A final velocity in the horizontal direction of 20 meters a second, that would be Vx, because that's what it was struck off the top of the cliff with, because there's no acceleration in the X direction, so it's not going to change. Calculate the magnitude and the direction, oh yeah, of the resultant velocity. So basically we're combining these two vectors back together. As is always the case, a diagram will always help you. As we've got there, we've got a vertical velocity there of 39 going down, a horizontal velocity of 20. These are the final velocities when it hits the ground at the bottom of the cliff. Remember, 80 meters out from the base of the cliff. We're wanting to work out the resulting vector there. How do we do that one? We've got two vectors, two sides of a triangle, which is there and there. Put them all together using Pythagoras. So that should be middle school maths for you. Should be pretty straightforward. If that's a challenge for you now, go and practice a few of these questions at the end of the chapter. Plug in your numbers. So we've got 39.2 was the vertical, 20 was the horizontal. Do our Pythagoras theorem, and that tells us that The combined vector is 44. So that tells us this number here. Now, what are we talking about? We're talking about velocities, so it's in meters per second. So 44 meters per second is the velocity it hits the ground with. Remember, about, 28, 29 meters per second is 100 kilometers an hour. So we're going relatively fast. Now we need to find that last little angle that's down the bottom of that triangle there, and it's just our trigonometric ratios. So tan is opposite over adjacent, which is your 39 over 20. Tan theta equals that. Bring your tan over the other side, make it inverse tan like we've got in these line here. Plug it into your calculator and it all comes out in the wash, 63 degrees. Now notice that that was from here, where am I? Here on our triangle, and the base of that triangle, which is Vx, it's written there, represents the ground. Vy represents like the cliff. You can kind of think about it that way. That means that our angle that we're finding is to the ground. So notice what we've written down the bottom here. The impact velocity is 44 meters per second at 63 degrees to the horizontal. Note the to the horizontal bit, so we know that there's a frame of reference for what we're doing. We have a magnitude and we have a direction. That's how hard the ball hits the ground and the angle it does it at. That's a very typical question that you'll have to do. Will you be likely to do these in your external exam? Absolutely. Okay, a little bit more work on this one. Here's old William Shatner throwing his rock at the Gorn, if you're into Star Trek. A rock is thrown horizontally at 35 meters per second off a cliff that's 75 meters high. Determine the rock's velocity when it impacts the ground. Very typical question here. Determine, it's basically like work it out with a calculation, a bit like a math stuff. But the determine part means that we've got to do several steps in here. We've got to put all this together. We know that the horizontal speed and we know that the height of the cliff, we've got to determine this impact velocity, which is going to be a magnitude and a direction. So let's write down what we know. We know our initial velocity is 35 meters per second because it told us up here. We know in the y direction it's 0 because it's just thrown off a cliff. It doesn't say any angle of projection or anything like that, so therefore it's 0. We know what g is because that doesn't change, not unless you're changing planets. And we know that the height of the cliff, the displacement in the y direction, is negative 75 because it's going down from our original starting point. Our original starting point at the top of the cliff being 0. What have we got to find? Final velocity. So what we need is an x and y component. X direction doesn't change because there's no acceleration in x, so that stays the same. The y component, here's a nice little formula. V equals u plus at, v squared equals u squared plus 2as. So velocity in the y direction squared equals initial velocity in the y direction squared plus 2 times g times the displacement, which is the height of the cliff. Plug your numbers in. So they're written all up the top here. They all just go into that equation, which goes into that bit there, and that goes into your hot little calculator, and it all comes out in the wash when you do the middle school maths. There. So even though we're doing what's grade 12 work, it's middle school maths really at this point. Once you put all that into calculator, what do we get? 38.4 is the y direction. So what are we going to do now? We have an x component, which we had up here. We had a y component down there. We're going to put them all back together and resolve the vectors back into one and find an angle. So here's my diagram. My y component, my x component, which I'm going to put back together as one triangle here. First step, as we did it before, is Pythagoras. I know the length of this side of the triangle, the length of this side of the triangle. I'm finding that one. C squared equals a squared plus b squared is what we've done down here. The numbers went in there. It went into our calculator. 59.1 meters per second is our final velocity. Remember, 100 kilometers an hour is what? About 28, 29 meters per second. We're going 51.9, relatively fast. The last step is the angle, and you can see up here we're doing the angle to the ground, which is my tan ratio, opposite over adjacent, which is what I've done there. Plug your numbers in. Again, if that middle school maths is a bit of a mystery to you, go and practice a few of the questions, come back and look at the example here, go back to your questions, check your answers, and make sure you've got it straight in your head. This should be routine by the time you finish this chapter. And by the time you get to the external exam, you should be able to do it in your sleep. The last part here is to write our answer out and combine everything back together. We've got a magnitude, 52. We've got a direction, 48 to the horizontal. Oh yeah, there's our final answer. Again, if you want to have a go at the other questions, have a go at that. One more thing that's important is to do some graphs and show how graphically what's going on with these things. So if I look at my graph here, you can see on the left-hand side there, I've got displacement horizontal versus time. So this is my horizontal displacement. You can see that's increasing at a linear rate. So there is no acceleration in the horizontal component, the extra component. Whereas in my y component, you can see that the vertical displacement is increasing over time. If we look at the distance between that one there and that one there at between 1 and 2 seconds, look at that distance in there, and then look at between 4 and 5 seconds, that distance is much, much greater. That's the displacement is increasing. Therefore, there must be an acceleration, there must be a force applied. It's coming from gravity. Whereas in this scenario here, I'm now talking about velocities. My horizontal velocity is not changing over time. It's the same number over time. Therefore, there's no acceleration in the horizontal direction, which is what we know to be true in these situations around Earth. Very, very classical physics. Whereas in the vertical direction, we can see that the vertical velocity is changing, and notice that the magnitude goes from 0 up to negative 50. So the magnitude is changing to 50, but it's going in the negative direction, and we should understand the negative direction is down. So the object is going down and accelerating down. Obviously, the acceleration is due to gravity. It's getting faster and faster. It's an object in free fall. All right, so we've done our work here today. We've looked at dealing with our vectors. We can describe the motion of an object in X and Y direction, pull it apart, put it back together. That means we have finished off all our curriculum objectives that are listed there. Those are literally the things that you need to be able to do for your external exam, and the external exam questions will be written based on only being able to do those things there. What's your job now? To throw your golf clubs in the lake. No. We've done all our equations there. Have a crack at doing some check your learning questions, practice work, questions at the end of the textbook section, other worksheets that you've got made available to you. Practice the work so you make sure you understand. Alrighty, thanks a lot for coming.